Welcome. Today we're going to talk a little bit about open loop and closed loop performance. Okay. So we've been talking about our electric motor. We have a picture of our electric motor. I've passed out kind of a detailed analysis about how you work it with the gears and all that sort of thing. And what we've come down to is that we've got a block diagram for our system, and it looks something like this. Here's what the block diagram is. We've got an input voltage that comes in. We've got a we went through the trouble to neglect the inductance on our motor, and so we have the motor torque constant Km. We have a resistance on the winding Rm. I've chosen to use the gear radii R2 over R1, and what this does is this puts out the torque from the motor. Now, the torque on the motor gets applied to the shaft, and what I've been doing is also saying that there's a disturbance force on the output of this thing. So I'm going to put a plus and a plus, a disturbance force on the output of the motor shaft. That may be something that you grab a hold of the motor shaft and just turn it. That's fine. Now, the dynamic parts of the motor we've developed look like this. 1 over J equivalent S plus B equivalent. Now, these dynamics relate the motor speed, which is theta dot, as the output. In this analysis, I'm just going to pretend like all we want to do is control the speed of the motor, although I want to point out to you that in homework assignments, the homework assignment that I'm going to give you for this problem, what we're going to do here is we're going to say here is theta dot. We're going to add one more block here, which is the integration from theta dot to theta as the output. But right now we're not going to do this. So one of the things that we're going to look at is let's look at what the open loop looks like. So open loop just means what I'm going to do is I'm going to apply a voltage, and I'm going to watch the output of the motor shaft. So for open loop, I'm just going to look at this as my transfer function, and what I'm going to see is I'm going to see that omega is equal to Vn Km over Rm, R2 over R1. And I'm going to rearrange this ever so slightly. I'm going to rearrange this to look like 1 over B equivalent. J equivalent over B equivalent S plus 1. And this has got to be a 1 over B equivalent. So what I've done here is I put a B equivalent up at the top there. I should make that clear. So I'm gonna make it here just as B equivalent. This is 1, and this is 1 over B equivalent. I just chose to do that because that puts this into the form of 1 over tau S plus 1, so that we know what the time constant for that system is. Now, what I'm going to look at the steady state. I'm going to look at the steady state output. So steady state output means when S equals 0. And what I see is that the steady state, I'm going to call this omega, is equal to Vn Km over Rm R2 over R1, 1 over B equivalent. So if I want this speed to go to a specific speed, if I want the motor to go to a specific speed, omega star, what I can do is I can do VI star is equal to omega star, right? So I can just, once I know what Km are, once I know all these numbers, I can measure these. The motor torque constant, that comes from the specifications, but we can measure it too. We'll talk about that. So what I can do is I'll just put this over 1 over Km over Rm, R2 over R1, 1 over B equivalent times omega star. So if I want to put that out, it's perfect. It's perfect. And now I'm going to make a little bit of a slightly different, I'm going to add something to this block diagram. Just to this open loop block diagram, I'm going to add something to it. And I'm going to say that this is going to be my omega star. Sometimes I call it omega desired, but for now I'll just call it omega star. That's what I want. And what I can do is I can just go ahead and, in block diagram parlance, I'm just going to find out what the error is here. This is E. And what I can say is that E, the error, equals omega star minus omega. And in this case, again, let's look. All this stuff is just constants. I'm going to call that C. Moreover, these constants, they're slightly different than the actual motor constants, right? Because the motor constants, maybe I didn't measure them quite right. So a lot of times I put a little hats over these just to let you know that these are the ones that I calculate as best I can. And there's always a little bit of an error involved there. And so what I find is that, I made one little bit of a mistake here. Omega, no, that's all right. So this is the same as saying here, omega star over C hat. So what is omega? So I know what omega star is, but what is omega? So omega is equal to, this is omega star, so that's what I want it to be. And I know what omega is. Omega is the voltage times C. It's voltage times C. So that's going to be minus. And the voltage is omega star over C hat times C. And this is going to be equal to 0 as long as C equals C hat. So that's an important thing. So as long as we've measured everything, our error is 0. That's going to be kind of important in the next, there's some in the next understanding of it all. So now I'm going to draw a different block diagram. This is going to be the closed loop block diagram. Closed loop block diagram. And the closed loop block diagram, now I'm going to use my magic control law. And the magic, so here I'm going to draw, first I'm going to draw, I'm going to do this. This is going to be Km over Rm, R2 over R1. So for right now, I'd like to leave this disturbance force in here, even though we're going to ignore it in just 1 second. And I'm going to call this is going to be 1 over B equivalent divided by tau S plus 1. And then here's omega comes out. And in this case, tau is equal to J equivalent over B equivalent. Right? So we've got that. J equivalent over B equivalent. What comes in here is Vn. And for my magic control law, like I say, all times magic control laws, we know how to make that magic control law. We say that it's going to be some proportional gain, some gain, and what we're going to multiply that gain by is omega desired. In this case, I'm going to say omega star plus, and then I'm going to subtract minus omega. And in this case, I can just connect those two things. And sure enough, I see that I have a loop. And I'm going to boil that loop down. It's going to be the feed forward. The transfer function, T of S, is equal to the feed forward, Kp, Km, over Rm, R2 over R1, 1 over B equivalent, divided by tau S plus 1, divided by 1 plus the feed forward times the feedback, Km, over Rm, R2 over R1, 1 over B equivalent, tau S plus 1. And then I'm just going to multiply by tau S plus 1. To clear these fractions, there's another formula we can learn later, but for now this is good enough. If there's only one formula that you have to learn, this is the one to learn. And that tells me that my transfer function, T of S, is equal to, I've made some other changes, and I'm just gonna do this now. I'm gonna call this one. Oh, let me make it in red so we can do it. Okay. I'm gonna call this C1, and I'm gonna call this one up here C2. So clearly, C is equal to C1 times C2, right? So I'm doing this for now just so we can kind of keep an idea of what's going on here. And so what I'm going to do is just write this transfer function. In this case, the transfer function is the output over the input, which is the output is omega, and the input is omega star, the desired one. And that transfer function is going to be Kp times C over tau S plus 1 plus C Kp. And what we're going to look for, again, we're going to look for the steady state output. Steady state. Sorry, I'm losing a little bit of my steady state output. I never manage my space quite right, but let's see what the error is equal to. In this case, we don't have to actually generate the error. We have the error, it's right there. The error is omega star minus omega. And if I plug in what omega is, in this case, omega is going to be, so this is omega star. And if I plug in what omega is just going to be omega star times C divided by 1 plus it's CKP divided by 1 plus CKP. Now, so this is going to be let's see. So this is omega star times 1 minus C Kp over 1 plus C Kp. Oh, there's some algebra that we have to do for this. this is going to be, so I'm gonna go this way with it. This is omega, because I'm running out of room down here. I'm trying to save just a little bit of room for it's omega star. This is 1 plus CKP minus CKP over 1 plus CKP, right? So I put both of them on the same. So if I have 1 plus CKP minus CKP, that means that the error is equal to omega star, whatever I desire it to be, times 1 over 1 plus CKP. So there's always a little bit of error. This is greater than 0. You might say, hey, wait a minute. This one's got a 0 error, and this one's greater than 0 for all values of KP, right? Because except one value of KP. When KP is really, really big, then the error goes to 0. So one thing that happens is when we use the closed loop formula, one thing that happens is that all of a sudden we realize that the input to our system is no longer, oh, we have to go figure out what the voltage is. No, we can just put directly into it what is my desired speed. However, you know, if I have everything right with my constants, I don't have any error. And this one I have a little bit of error, but I have to make KP bigger. So maybe this is a special case. It turns out that this is a special case. This is what's known as a type 0 system. There's no free integrators. No free integrators. So later, that's a free integrator. So when we look at a motor, when we're trying to make it go to a specific position rather than a specific velocity, we see that there will be one free integrator, and we're going to call that a type 1 system. All right, so let me go on for one moment then, and what we're going to do is we're going to look at the effects of feedback on transistors. How does feedback change the dynamic response? How does it? Well, let's go back and look at our both our open loop and closed loop transfer functions. The open loop transfer function, T open loop, is equal to C over tau S plus 1. And this is open loop. And here's closed loop. Here's the closed loop transfer function. It says that T of S, I should have done this. This is the output over the input. This is omega over omega star. In this case, the output over the input on this one is a little bit different. This is, the output is omega and the input is VI. So that's open loop. And in this case, omega over omega star, it is KP C over tau S plus 1 plus C KP. And another way that I can write this, so this one, if I just want to look, I can just go find out what tau is. Tau is equal to, I have to go look and see what my tau is. Tau is J equivalent over B equivalent. These are mechanical parameters. So in order to change these, that costs money. You have to go buy a new motor or something, right? And So now I'm going to look at this time constant. So I'm going to put this into a different form of the time constant. That says that T of S is equal to omega over omega star, which is going to be Kp times C divided by 1 plus Kp times C divided by tau over C Kp plus 1. Sorry, I put that in the wrong order. S plus 1. So I just get this into, and now what I can see is this is tau nu. And look what happens here. Tau nu is always less than tau. So the time constant is always less. So if I wanted to draw this response as a function of time, you know, I'm going to put them both on. Some of my notes I don't do it that way, but I'm going to put them all on the same one. So this is omega, and this is time. And for the open loop, what I can do is I can say this is 1 times the time constant, 2 times the time constant, 3 times the time constant, and 4 times the time constant. So I know that by the time I get to the 4 times the time constant, my output now is its steady state. So 1 times the time constant, it goes about 63% of its final value. Twice the time constant, we just put a dot that's a little closer and a little closer, and then by the time we get to the time, 4 times the time constant, it's less than 2% off. There's still less than 2% more motion to go, and then we can just draw this in. And where is this steady state value now? So if C is equal to C hat, then this is omega star. Okay, we're going to talk about that assumption in a moment. And so this one is open loop. Now, the whole point of open loop versus closed loop is that in the closed loop, I'm going to go back and just show you this other, in the closed loop system, this Kp is something that you get to choose as the system designer. You're the control system designer. You get to choose Kp. What value do you choose Kp as? Well, one thing in this page, we found out Kp should be large. Does it need to be large? Well, when Kp is 0, you just get this response. When Kp is some number, tau nu is less than tau. So what we can do is we happen to know for sure. I'm going to make it in red so we can see it here. This is Kp1. It's faster. And if I make Kp bigger, let's call that Kp2. So what I've done is there's a slight little bit of difference here, and that is, let's look at closed loop steady state. That means S equals 0. So closed loop steady state is Kp T S equals 0 is equal to Kp is Kp times C over 1 plus Kp times C. So what we see is that this one is just, for all Kp's, this is just a little bit less than 1. And so what I should have done is that I kind of made this one actually settles in a different spot. I'm going to scratch that out. This one, when Kp gets bigger, the spot that it settles to is closer, right? So let's say Kp is equal to 1, Kp equals 1, then this is T, the steady state, is equal to C over 1 plus C. when Kp is equal to 2, then this is going to be T steady state is going to be, let's make it 10. That'll make it easier. It's going to be 10C over 1 plus 10C. And when Kp is equal to infinity, it's equal, then T steady state is equal to 1. So we actually have to make that really, really big in order to eliminate this tiny amount, this amount of steady state error. We're going to see that's a little bit different on our motor, but that's an important piece of it is to think about. So how does feedback change the dynamic response? It can improve the response. Well, we'll find it can improve the response. We'll find that that isn't always the case. Okay, now let's take a look at what happens. Now, I purposely wanted to add, keep all that stuff about the disturbances on there. So what about disturbances? What about disturbances? Well, let's go back and look at the open loop system again. I'm going to look at the open loop system. VI is equal to Km over Rm, R2 over R1. Right, here's D. And here is 1 over B equivalent tau S plus 1. Sometimes I call this one C1, and sometimes I call this one C2. So here's the open loop system. So in this case, the open loop system, what I'm gonna try and emphasize to you is that the open loop system doesn't have anything to do with Vn anymore. So now I've got my motor going at the right speed, omega. I've calculated, right? I've gone back and I calculate, oh, what is the perfect voltage to make this thing go at the perfect speed? But now somebody grabs a hold of the motor shaft, and this is what the open loop system looks like. So the open loop system, I'm going to call this T sub D open loop. The disturbance open loop control system is just going to be C2 over tau S plus 1. And if I look at what the dynamic, this is the open loop system where this is omega as a function of D. And so when I look at the steady state, if somebody grabs a hold of the motor shaft after I get the motor going at exactly the right speed, then what I can see is that the output, omega over D, is equal to C2. So no matter what happens, there is error. Yes, error. Now I'm going to look at closed loop. I'm going to look at the closed loop system again. I'm just going to write it this way. C1. Here's D. Here's C2 over tau S plus 1. So now I'm just kind of reverting back to control system lingo. You know, I'm going to keep doing this in a different color just because I want to emphasize that this is the controller that we're putting together here. This is omega desired plus, and this is omega minus. So here's my closed loop system. And we've already done this. Well, let's do it again. I want to emphasize again, this time also, this is the feed forward part. In fact, you know what I'm going to do? just to make this crystal clear, I'm going to redraw this block diagram ever so slightly. So here's D comes in here. This is a plus. And then also what comes in here plus is, this is going to be C1, right? So I'm going to put this C1 comes in there. I'm going to put this KP comes in there. And then what I'm going to do is I'm going to put, here is omega, that's a minus sign, and here is omega desired, that's a plus sign. I'm putting it down there. And now what I'm going to do is I'm going to redraw this. This is just going to be C2 over tau S plus 1. Omega. Okay? So I've just redrawn the block diagram. I redrew it this way so that you can clearly see that that's the feed forward. And if you need something that's a feedback, here is the feedback term here. Right? Now, I'm going to do some tricks. I'm going to play some tricks. So what I'm going to do is I'm going to say, you know what? I've already commanded my omega desired. And you know what I can just do? I can just command it to be 0 if I want to. And then I'm going to see what happens. If it's 0 and I put a disturbance force on it, I'm going to see what happens. Now, one thing is that when I take this omega and put it into a negative summing junction here, I could also just do this. Oops. I could also just do this. -1, and then I get to change that to a plus. And since this is 0 anyway, I don't even care. I'm just going to move my -1 here. Whoop. And then for now, this is 0. I'm just going to go ahead and move my -1 here. Okay. So I've kind of just done some minus sign stuff here. But now I'm going to go back and let's figure out what the transfer function is. TD closed loop is equal to the output over the input. And in this case, it's going to be the feed forward, C2 over tau S plus 1, divided by 1 plus the feed forward, C2 over tau S plus 1, times, it's the feed forward, 1 plus the feed forward, times the feedback, which is, remember what this plus and minus has to do with. I already fiddled around with these pluses and minuses, so this is okay. I'm going to scratch that out. It's 1 plus the feed forward times the feedback, which is C1 KP. Okay? And let's clear this tau S plus 1, tau S plus 1, and then what we get is that T, for the disturbance, the closed loop transfer function, how does the velocity change as a function of the disturbance that I apply? It's going to be equal to C2 over tau S plus 1 plus C1 C2 KP, which is C2 over let me just do this. The TCL closed loop, S equals 0, that's steady state. Right, that's steady state, is going to be C2 over 1 plus C1 C2 KP. So there's some finite error on here. But remember, we choose KP. And what did we choose it for? What did we want it? We wanted it to be big. And the bigger it gets, KP big gives me omega over D is small. Right? So if KP is big, it makes this whole thing small. And that's what I want. Hey, if you grab hold of the end of my motor, I don't want it to slow down. I want it to keep going. And that's what it does. So what about disturbances? Closed loop reduces the effects of disturbances. Let's do one last thing here. So I mentioned earlier parameter errors. What about parameter errors? How about with parameter errors? Okay, so let's just say, you know, my statement earlier was that we're really good engineers and we know how to measure all the parameters on the system. But let's just say, for the instance, that so the equivalent damping, which is the equivalent damping is B out plus BM R2 over R1 squared. It's the gear ratio squared plus KE KM over RM times R2 over R1 squared. So one thing I want to point out is that even if there's no motor or output damping, we still get some electrical damping that has to do with the back EMF. So in some of our problems, we just ignore these things. But what if we can't ignore these things? And that the real B equivalent is equal to twice what we estimate the B equivalent to be. Right? So now we're going to say, oh, if it's open loop, what I can say is that T of S equals 0, this is the steady state, is equal to the it's equal to the output, which is what did we want it to be. And what we did was we already calculated that the output of this has to be 1 over B equivalent times C1. Right? So we calculate. Earlier, we said, oh, well, I can calculate how much the voltage needs to be. And now I'm going to run it through my system. So this is the system, is this 1 over 2 B equivalent. So the actual system is twice 1 over the system. So this is the assumed value to compute V star, the voltage. But this is the actual value in the motor. Right? So they're different. And so what we see is that omega out is omega star over 2. And so how much error is that? Error is equal to omega star minus omega out over omega star. So if I want it in percent error, if I wanted to try and get it in percent error, this is going to be omega star minus omega star over 2 divided by omega star, which is going to be 1 minus 1/2 equals 0.5, 50% error. Wow. So if I just miscalculate one of my motor parameters, I get a pretty good size error on there. But what about with closed loop? How about with closed loop? Well, why don't we look at that? We already know what the transfer function for this is. The closed loop transfer function is omega over omega star, and that's going to be Kp C1 1 over 2 B equivalent hat. That's what's really in the motor, and this is divided by tau S plus 1 plus C1 1 over 2 B equivalent hat times Kp. So this one, we never did use the assumed damping value, the parameter value. We never used it. We just put our controller around it and we calculate what this stuff is. And so what we can do is we'll say like the steady state output, T of S equals 0 is the steady state output, which is omega out over omega star. I'll call this omega steady state. So then I can rewrite this equation a little bit different. Omega steady state is equal to omega star times T of S equals 0. S equals 0, which is going to be S equals 0, Kp, C1, 1 over 2 B equivalent hat, divided by 1 plus C1, 1 over 2 B equivalent hat, times Kp. Now you'll notice this is almost 1, but not quite 1. Why do we want it to be 1? Why do we want T of S equals 0 to equal 1? Because what that does is that means omega over omega star, the actual output divided by our desired input, is equal to 1, and that tells us omega equals omega star. Oh, that would be perfect, right? Because then we say, hey, go to this speed, and it goes to that speed. And now what we're going to do is we'll say, oh, by the way, I can look at this, and I can see that this is for choose, we already said this, to choose Kp equals big. And that makes the steady state error go to 1, right? Because the steady state error goes to 1, if that's big. Okay, so what have we learned here? What we've learned is, and this is going to be on the exam, so this is something that you want to remember all the time. Why use feedback control? 1, it reduces steady state error. Now, in this one, because it was a type 0 system, it was a little weird, right? Because for type 0, the open loop gave us a perfect one. And when we put the feedback gain on there, we had to make the gain pretty big. So it does reduce steady state error. We'll see that that's more true, better with type 1. Okay, it reduces steady state error. So we got that one, right? Now let's see what else it does. It improves the dynamic response. Right? So we saw that. Oh, we can make it faster and faster. 3, it reduces the effects of disturbances. 4, it reduces the effects, I'll spell it right this time, of parameter errors. So, if I should say on an exam, it says, name 4 reasons to use error feedback control. Sometimes it's called error feedback control. 1, 2, 3, 4. These are the reasons that you're taking this class. This is what this is good for. And here's the 4 reasons. Okay? All right then.